of ammonia, NH3. And based on our topic, so this is the Lewis dot structure for ammonia. So we call this one actually Lewis dot dash structure. So when you look at these two molecules, the first one, it says in ammonia molecule there is nitrogen and 3 hydrogens. So that is all it says just by looking at the molecule. If you look at the Lewis dot structure, it says there is nitrogen and 3 hydrogens, and the nitrogen is in the middle and the hydrogens are terminal atoms, and nitrogen and hydrogen, between nitrogen and hydrogen there is a single bond, and there is a lone pair on nitrogen. So this pair is called the lone pair. So as you can see, when you write the Lewis dot structure, you can get more information compared to just writing the molecular formula. This is important, especially when you are going to decide the molecular geometry, how this molecule is arranged in 3D space. So writing Lewis dot structure is really important. So that is our topic today, Lewis dot structure, how to write a Lewis dot structure for a molecule. So let's start with the simple one and then move on. Let's go to like big molecules. So in Lewis dot structures, when writing Lewis dot structures, what we do is we represent the valence electrons of elements or molecules using dots. So that is why it is called dot structures. Let me write it down first. Now you may ask why we are looking at just valence electrons. Why not other electrons like co-electrons? The reason why is when elements make compounds, when elements make molecules, when elements make bonds, only valence electrons are being used. The co-electrons do not participate in bonding. Only valence electrons do. So that is why we are looking at valence electrons. So let's start with a simple one. Let's see how we can write a Lewis dot structure for an element, a simple element. Okay, let me write it in this way. So if you think about this one, it's really simple. Let's take an example. Let's say we are going to write the Lewis dot structure for sulfur. Since we are only looking at valence electrons, we need to know how many valence electrons sulfur has. Okay. It is really easy to find if you have a periodic table with you, or if you know where the elements are located in the periodic table. The sulfur is in group 6A to be right. Okay. So that means sulfur has valence electrons. So if I write it in this way, I assume you remember. For main group elements, so what are the main groups elements? The S block and P block. Those are the main groups. So this is very simple to remember. For main group elements, which is S block and P block elements, the number of valence electrons equal to the group number. Right? Just remember that way in that case, so you will remember it properly. So now let's go back to that sulfur. So sulfur has 6 valence electrons. It is in group 6. So let me write in this way, 6 valence electrons. If I write the Lewis dot structure for sulfur, it is really simple. So this is the symbol, and then you distribute these valence electrons around sulfur. First put 1 electron in all 4 sides, because there are 6 electrons, so we can do that. Okay, now we have put our 4 electrons, there are 2 left, and then you go back and pair 2 of those electrons, so that 6 is complete. So I can come here and pair this one and pair that one, like that. So this is the Lewis dot structure for sulfur. Very simple. Let's do another one. Let's take chlorine, Cl. Cl is in group 7, chlorine is in group 7, 7A. So that means it has 7 valence electrons. So if I write the Lewis dot structure, then this is the symbol. There are 7 electrons we have to distribute around Cl. So that is 4. There are 3 more. Then we can come back and pair 3 of these electrons. So now we do have 7 valence electrons. So that is the Lewis dot structure for Cl. Let's do one more, and then after that we will move on. Let's take sodium, for example. Argon is in group 8, 8A. So this is a noble gas. Argon is a noble gas. So this has 8 valence electrons. So if I write the configuration, the Lewis dot structure, it looks like this. So there are 8 electrons. We have to distribute them around argon. So first I'm going to distribute 4 electrons, and there are 4 left, and then I come back and pair these up. So that is the Lewis dot structure for argon. So you can do the same for ions if you want. Let's take this one, Cl minus. This is the anion of neutral chlorine. So it has 1 extra electron compared to neutral chlorine. So another way to say, this has 8 valence electron. Cl is in group 7 when it's a neutral element. The chloride ion, which is the Cl minus, it has an extra electron. It has taken an electron from somewhere else. So now it has 8 valence electrons. So if I write the Lewis dot structure for Cl minus, it looks like there are 8 electrons around it, and the charge is minus. So that is that simple. It is not that difficult to do. I assume you understood this part. So what is important is the how to write the Lewis dot structure of a molecule. So we are going to spend more time on that topic. So when you do Lewis dot structure for a molecule, so you have to consider different aspects. You have to consider lots of facts. So we will discuss them one by one, then it will be easier. So let me write it in under this topic. So how to write a Lewis dot structure of a molecule. So we just did elements. We did couple of examples. In that case, first thing we did was we figured out how many valence electrons that whatever the element in question has. So that is the first thing we figured out. You do the same when you write the Lewis dot structure for a molecule. You need to know how many valence electrons are there in the molecule. It is really easy to calculate. It's a very simple calculation. Okay? So let's do step by step. So the first thing you do, I'll write this in this way. I'll write step by step, and then we can do examples later. So the first thing you do, so the first step is you decide how many valence electrons are there in the molecule, the number of valence electrons in the molecule. So how do we do this? It's very simple. So what you do is you get the valence electrons of individual elements and add them up. So that will give you the number of valence electrons of the molecule. So let's take an example and do. Now let's take that NH3 we did before. So I'm going to calculate the total number of valence electrons of NH3. So nitrogen is in group 5A. So it will give you 5 valence electrons. I think you understand that. Next, hydrogen is in group 1, and it gives you 1 valence electron, and in the molecule there are 3 hydrogens. So your total is going to be the sum of these two, 5 plus 3, 8 valence electrons. So the molecule has 8 valence electrons. That is simple. So let's take another one, another example. Let's say I have this sulfur trioxide, SO3. Sulfur is in group 6A, so it will give you 6 valence electrons, and oxygen is also in group 6, so it will give you 6 valence electrons, but in the molecule there are 3 of them, so 6 times 3. So the total is going to be 18 plus 6, which is 24 valence electrons. Sulfur trioxide has 24 valence electrons. Let's take one more. Methane, CH4. Carbon is in group 4A, so 4 valence electrons, and hydrogen, we know it is in group 1 valence electrons, and there are 4 hydrogens in the molecule, so 1 times 4. So the total is going to be 8 valence electrons. So far we look at 3 examples, 3 molecules, and all those molecules are neutral molecules. You don't see a charge on the molecule, so those are neutral molecules. Now let's take a charged one. Let's take this polyatomic ion, let's say phosphate 3-. So in this molecule there is phosphorus and oxygen. We know phosphorus is in group 5, it is 5A, so it will give you 5 valence electrons. I don't think there is a question there, it is simple. Next, oxygen. Oxygen is in group 6 valence electron, and in the molecule there are 4 oxygen atoms, 6 times 4. So in this one, this is an ion, this is a polyatomic ion, phosphate ion. Since it is a negative ion, you add equivalent number of electrons into your total count. So that charge 3-, you have to take that into account when you count the number of valence electrons of the molecule. So let me write in this way so that you understand it. Since it is a negative ion, you add the electrons. How many? It is equal to the charge. So the charge is 3, so you add 3 electrons. Now the total is going to be sum of all these, so it is 5 plus 6 times 6 times 4, 24 plus 5, 29 plus 3, 32 valence electrons. So let me write it in words so that when you read this you understand. So again, keep that in mind, you add electrons when it is a negative ion. So let's do couple of examples just to make this point. Let's take this ion, carbonate, CO3 2-. So carbon is in group 4 valence electrons, we know that by now. Oxygen is in group 6 valence electrons, and there are 3 oxygens in the molecule, and this carbonate is a negative ion. For the ion, we have to take that into account. For the ion, we add 2 electrons because it is a negative ion and the charge is 2. So the total is going to be 18, 20, 24. So carbonate polyatomic ion has 24 valence electrons. Let's take one more, another negatively charged ion, SO4 2-. Sulphur, 6 valence electrons. At this point we know sulphur is in group 6, so 6 valence electrons. Oxygen, the same group, but there are 4 oxygens, and for the anion we add 2 electrons. Why? Because the charge is negative 2. So the total is going to be 32 valence. So at this point I think you got this point, how to calculate the number of valence electrons. So far we discussed neutral molecules and negatively charged ion. Let's look at positively charged ions. If the ion is a positively charged ion, how are we going to do the electron count? Let me take an example like this. Say this ammonium ion, NH4+. In this case, nitrogen is in group 5 valence electrons. Hydrogen is in group 1 valence electrons, and there are 4 hydrogens, so times 4. So now we have to account for the plus charge, positive charge. If it is a positively charged ion, you subtract electrons. You subtract electrons from the total count. How many electrons? It's equal to the charge. So in NH4 it is plus 1. That means you have to subtract just 1 electron. For the positive ion, so you have to take that into account. You subtract 1 electron. So the total is going to be 9 minus 1, which is 8 valence electrons. Let's look at another one, SO2+. Let's say we have that kind of molecule. So sulfur is in group 6 valence electrons. Oxygen again in 6 valence electrons, and there are 2 oxygens in the molecule. So this is a positive ion. We have to account for that. You subtract 1 electron because the charge is 1, positive 1. So now then, total electron count, valence electron count for SO2 plus is 18 minus 1, which is 17 valence electrons. So I assume you got this point. This is important. This is a very simple thing to understand, but it is important when you write in the Lewis dot structure. So that is the first step. So the next step is, so let's say it is 2. So the step 2 is you have to decide what the central atom is. In Lewis dot structure, the arrangement is there is a central atom and then there are terminal or peripheral atoms. Next step is, once you decide the number of valence electrons, next thing you have to decide is what is going to be the central atom. It is really easy to decide. So next thing is then decide the central atom. So how do we decide this one? For example, this NH3, nitrogen is the central atom. SO4 2 minus, if I draw the Lewis dot structure for SO4 2 minus sulfate ion, sulfur is the central atom. If I do, let's say CH4, carbon is the central atom. So I knew it. How do I know it? So this is how we decide. It's easy to decide. Just remember these 2 facts before we decide the central atom. Hydrogen and fluorine, the group 7 element fluorine, they do not sit in the middle. So they will be terminal atoms. That is one thing to understand. The least electronegative element in the molecule. If you don't know what electronegativity means, so let's very quickly look at a couple of elements. I'll tell you a trend. The least electronegative element in the molecule is going to be the central atom. So let me write it down. After that we will discuss. So what is electronegativity? If you don't know what electronegativity means, please check that topic. Okay. So basically it is like ability to attract electron. How much these elements like electron. In the periodic table there is a trend, but I'm not going to talk about that trend here. But when you read about the electronegativity, so just focus on the trend as well. We call it periodic trends. There are couple of elements in the periodic table that you need to know. When you see fluorine, for example, you need to know it is the most electronegative element in the periodic table. When you see oxygen, you need to know it is the second most electronegative element in the periodic table. Likewise, there are a couple of elements you need to know in back of your head. Okay? So if you see fluorine, that is the most electronegative element. Let me write it in this way. Then oxygen, then nitrogen and chlorine. So these last 2, nitrogen and chlorine, they do have a very close electronegativity. Okay? In some books you will see after oxygen chlorine comes in. After chlorine it is nitrogen. But they do have a very similar electronegativity values. Okay? In this direction, when you go from fluorine to chlorine or nitrogen, electronegativity decreases. So the least electronegative element will be in the center. If you look at this sulfate ion here, it is with oxygen, right? There are 4 oxygen, 1 sulfur. So oxygen is the second most electronegative element. That means definitely electronegativity of sulfur is smaller, less than the oxygen. So sulfur is going to be in the center. The other way to see this one or decide this one is for most molecules. For most molecules, the first element in the molecule is the central atom. If you look at this example, NH3, nitrogen is the central atom. Sulfate, this is 2 minus, I'm sorry. Sulfate, sulfur is the central atom. Methane, carbon is the central atom. For most molecules, first element is the central atom. So that is another way to decide this one. So now so far we discussed how to calculate the number of valence electrons and then how to decide the central atom. Once you decide the central atoms, the other atoms are going to be terminal atoms. These should be placed around the central atom. So let's write this way. Before I move on, let me say this way. So in here I'm saying for most molecule, first element is the central atom. But if you take a molecule like this, water molecule, the first element is 2 hydrogens, but they are not the central atom, not central. So remember I mentioned that point, hydrogen is not going to be the central atom. So for water, oxygen is the central atom. The other way to decide this one is for most molecules. Okay? So the central atom, there is only one central atom. The others are going to be terminal atoms. For example, in NH3, there are 3 hydrogens, so they are terminal. For sulfate, there are 4 oxygens, so oxygens are terminal atoms. For CH4, hydrogens are terminal atoms. So you can decide that way too. So, okay, there are several ways to decide the central atom. So the next thing is, let's say it is 3. So once you know the central atom, what you do is you just draw the molecule. You draw the skeleton structure of the molecule. You know the central atom, you know the terminal atoms. You just sketch a skeleton for the molecule. Let me write it in this way. So let's see what it says. So the next thing is draw the skeletal structure of the molecule by connecting the central atom with terminal atoms using a single line. So what I mean by that is, let's take an example. Let's take this sulfate ion. So we decided sulfur is the central atom. So there are 4 oxygens around it. So this is 1, 2, 3 and 4. Then what you do, you create a single line between the central atom and your terminal atom. So oxygen are the terminal atoms. So this is the skeletal structure. So each line in this topic, each line is 2 electrons. So I can draw this one in this way as well, just to make it clear. So you have the central atom sulfur, and then you have oxygens as terminal atoms, and then in the skeletal structure, so we have 2 electrons here, another 2 there. Why? Because each of these line is 2 electrons. So the next step is, so let's say it is 4. Once you have the skeletal structure, remember in the first step we calculated the number of valence electrons, total number of valence electrons. Then you are going to distribute those electrons on the atoms of the molecule. So now in this one, when you make that skeletal structure, I said each line is 2 electrons. That means for this sulfate you created 4 lines, right? That means you used 8 electrons, 4 times 2, to create those 4 lines. I assume you understand, you are following what I am saying, right? Each line is 2 electrons and we created 4 lines, so total is 8 electrons. So that means out of the total valence electrons, we used 8 to create those lines. The total number of valence electrons for sulfur we calculated here. I assume, yes, it is 32 valence electrons. So once you make that skeletal structure, out of that 32, there were 32 valence electrons at the beginning, and then we used 8 to create those lines. Now what is left is 24 valence electrons. So in the next step, what you do is you take those electrons, whatever the leftover electrons, and complete the octet of terminal atoms, starting from the most electronegative one. So what is octet? Octet means 8 electrons. You take whatever the leftover valence electrons and go to terminal atoms and complete their octet. Give them 8 electrons. So you do this, you start from most electronegative element. In sulfate, all 4 terminal atoms are the same, oxygen. Doesn't matter which oxygen you choose first. So that is the 4th step. So let's do it for sulfate while we are doing this one. So this is sulfur. It is in the middle. Now I have my skeletal structure, which is this. To create this one, I used 8 electrons. There are 24 left. Now you go to terminal atoms and complete their octet. At this point, this oxygen already has 2 electrons. The electrons in this line, the electron represented by that line, belongs to oxygen as well as sulfur. So at this point, oxygen has 2 electrons. So to complete the 8, we need to give it another 6. So I can place 6 electrons on oxygen. We place them as pairs. So place 6. So there are, remember, there are 24 left here. So we can do the same for this oxygen. 12. We can do the same for the other 2 oxygens. So now we had 24 electrons left. Out of those 24, I placed 24 on this oxygen. Now I have nothing left. So 0 valence electrons. But we are not done here yet. So now if we check, once you do this one, you have to check whether your elements have 8 electrons. All the oxygens have 8 electrons. The sulfur has 8 electrons, but still this is not the right structure. So let me put the charge here. It is 2 minus. Let me do. So this is not the right structure. So next thing you need to check is, let's say it is 5. So you have to check something called formal charges. You have to check the formal charges of elements. So I'll tell you what formal charge is, how to calculate or how to figure out the formal charge in a second. So what this formal charge is, or how to calculate formal charge is, what you do is, you take the particular element. For example, let's say you calculate the formal charge of sulfur. So you look at sulfur. Okay? Then you use this formula to calculate the formal charge. The formal charge of given element, it's given by this equation. It is the number of valence electrons of that particular element minus, so let's see whether we can understand it. For example, let's say I'm going to calculate the formal charge of sulfur. Now the formal charge of sulfur equals to the number of valence electrons of sulfur which you get from the periodic table. The group number equals to the number of valence electrons minus the number of lone pair electrons on sulfur, or whatever the element in question, minus half of the bonding electrons. I have written it positive here because I have put both in within brackets. Otherwise you subtract those two. When you do an example, you will see it. Now you need to know what are lone pairs, what are bonding electrons. Okay? So I assume you understand the formula. So in this molecule, so this is what we have so far. So now I am going to calculate the formal charge of sulfur. First thing is, you need the number of valence electrons of sulfur, which is coming from the periodic table. Sulfur is in group 6, so it is 6, minus the number of lone pair electrons on the element, in this case on sulfur. You don't see any dots on sulfur. So these electrons, these are called lone pair electrons. The paired dots, these ones, called lone pair electrons, because they are not making any bonds. They are not in a bond. They are just sitting there as pairs. So they are called lone pair electrons. Sometimes we call them non-bonding electrons. because they don't make any bonds, they are just sitting there. The bonding electrons are the electrons in the bond. So remember what I said, this line is 2 electrons. So there are 2 bonding electrons in that line. So there are 2. Let's keep that in mind. So since there are 4 bonds around sulfur, there are 8 bonding electrons. So for the formula, what we need is, we need the number of lone pair electrons, which is 0 for sulfur, plus half of the bonding electron. It is half, not the all, it is half. So around sulfur there are 4 bonds, each bond is 2 electrons, so there are 8 electrons, we need half of that. So it is going to be 4. So now the formal charge of sulfur is going to be positive 2, 6 minus 4, positive 2 in this molecule. If I calculate the formal charges of oxygen, let's calculate it. Oxygen is in group 6, so 6 valence electrons, and let's take one oxygen, doesn't matter, all 4 are the same in here. Okay. So if I take one, so there are 6 lone pair electrons, because you see those 6 dots, plus there is 1 bonding electrons. There are 2, but we need half. It is 6 minus 7, which is negative 1. For sulfur it is plus 2, oxygen negative 1. So you need to understand, if you calculate the formal charges of all 4 oxygens, they are going to be negative ones, each are negative ones. So that if I write it, this is formal charge is negative 1, this is negative 1, likewise all the others are negative 1, because they are the same. You can calculate and see. Sulfur is plus 2. So this is a red flag for me when I am looking at this one. When I see that positive formal charge on the central atom, it is a red flag. We should get rid of that if we can. There are some instances you cannot get rid of that, okay, violating any rules. If you can get rid of that, yeah, you should. Okay. But in this case you can. The other thing is, each and every atom has a formal charge. So we should minimize that distribution. We should try to make them zeros if we can, but not all. We can't make them all 0. So let me write it in this way. So this is the extension of number 5. Let's say it is 5b. So molecules like to have minimum distribution of formal charges. So in this one we have 4 negatives and 1 positive. So the central atoms don't like to have plus formal charge. We should try to make it to a 0. So how do we make it to 0? Let's write it in this way. So how do you make that central atom, the formal charge of central atom to 0? By making double bonds with terminal atoms. Okay. So I added this word if allowed. So because if you see halogens as terminal atoms, you can't make a double bond with the halogen. You know what halogens are? Those are group 7 elements. You can't make a double bond with terminal halogens. Okay, I'll write it down in a second, but just keep that in mind. The reason why is because of this point. So just pay attention to this point. Let me write it down first. After that I'll explain. Pay attention to this point here. The most electronegative atoms in the molecule cannot have positive formal charges. So if you see a formal charge, positive formal charge on oxygen for example, that is a red flag. So you have to recheck your molecule. Maybe something is wrong. If you see a positive formal charge on fluorine for example, it is a red flag, so you have to check it again. So most electronegative atom in the molecule cannot have the positive formal charge. So there are lots of information here, so you have to read this carefully, and when you do example, just pay attention. Okay, this is not difficult, but there are lots of information. Okay, let's go back to that sulfate ion. So we decided sulfur, at this point sulfur, the formal charge is +2. So we have to get rid of that. How do we do that? By making double bonds with the terminal atoms. So with oxygen we can do that. Okay? So this is what I have so far. So the formal charge of sulfur is +2. We have to get rid of that. So to do that, what we do is we make double bonds with the terminal atoms. The way you make that double bond is you take one of these pair of electrons and share it with sulfur. Just give it to the middle. If I do share just one pair of electrons from the oxygen, this is what I get, right? So remember what I said, each line is 2 electrons. Now we are giving 2 electrons sharing with sulfur. That means you are adding another line. So it is a double bond. Now you are making a double bond with this oxygen. So now what I have is, we did not do anything to these oxygens, and the one on the top, that oxygen we took a pair and shared with sulfur. That is how you made this second line, that double bond. Now this oxygen has 2 pairs left. So that is what you have. If you calculate the formal charge of sulfur again for this new molecule, for this sulfur, let's calculate. Let's calculate the formal charge of sulfur in this molecule. I'm just putting the numbers into this formula we discussed. So number of valence electrons 6, and we don't see any lone pairs on sulfur, we don't see any dots, so it is 0, plus number of bonding electrons, we need half of that. Now you see 5 lines, that means 10 electrons, we need half of that, so 5. 6 minus 5, it is +1, so still it is +1. So now as you can see, when we shared one pair of electron, the formal charge went down by 1. If you want to get rid of this +1, then what we can do is we can share another pair of electrons with sulfur. In that case we can make it to 0. So then let's say I'm going from here to there. So I'm going to share, let's say, this pair of electron with sulfur. So in that case what I get is, so this one doesn't change, this one doesn't change. So now there are 2 bonds here, this one doesn't change. So the electron distribution is like this. So now if you calculate the formal charge of sulfur, you will see it is 0. So if I calculate the formal charge of sulfur again, just to show, in this molecule it is again number of valence electrons 6 minus, we don't see any lone pairs. So now there are 12 bonding electrons, we need half of that. 6 minus 6, it is 0. So the formal charge of sulfur is 0. So now you can calculate the formal charges of oxygens as well. Now the oxygens are not, all 4 are not the same, right? They are different because 2 oxygens are bonded through double bonds. So this is called a double bond, and this is a single bond because there is single line, 2 electrons. So those oxygens are different. If you calculate the formal charges of oxygens, I'll calculate one. Let's say I'm going to calculate the formal charge of this oxygen. After that I'll let you calculate the others. So you just basically use the formula. Okay? So I'll say this is double bonded oxygen, so that you know which oxygen we are talking about. Number of valence electrons of oxygen is 6 because it is in group 6, and then that oxygen has 2 lone pairs, that means 4 lone pair electrons, and it has 2 bonds, which means 4 electrons. We need half of that, so it is 2. So 6 minus 6, it is 0. So the formal charge of this oxygen is 0. Then you should understand the formal charge of this oxygen is 0 as well, because they are similar. If you calculate the formal charges of other oxygens, this is going to be -1, this is going to be -1. So now the distribution, initially it was 4 minuses and +2. Now we minimized it to just 2 minuses. All the others are 0. So this is the right structure for sulfate ions, right Lewis dot structure. If I draw it to show you properly, so there is a double bonded oxygen here, double bonded oxygen there, and single bonded oxygen like that, and electron distribution is this, and this is the sulfate ion. So this is called the Lewis dot dash structure of sulfate. So if you need the Lewis dot structure, it's really simple to do. Basically, the double bond means there are 4 electrons. Those are the 4. Here again there are 4 electrons. Single bond means just 2 electrons. So it is 2 minus charge. So this is called the Lewis dot structure. Both are the same, both are similar, only the way we represent it is different. So I think so far we discussed everything, all the steps we have to discuss to come up with a right Lewis dot structure. Now it is time to put this into practice. So we have to do several examples just to make sure that we got this point.